This video lecture is section 6 of chapter 11, talking about phase diagrams in your textbook. We'll be talking about the basic construction of a phase diagram and what it looks like, and then how to interpret that for intermolecular forces. Phase diagram has a couple different features to it. First of all, it really shows you where the solid, liquid, and gas stages are, where the transitions are at, and where all three could possibly exist at any particular time. So a couple things to get familiar with it. Here at the bottom you've got the solid, which is to the left, gas is to the right, and then the liquid stage is here. Notice the transition between directly solid to a gas. You've got sublimation, gas back to a solid, deposition. Here's liquid to gas is vaporization, condensation back is condensation is going to be gas back to the liquid. Solid to liquid is melting. Liquid back to solid is freezing. All of these are respective of intermolecular forces and when they can lie in between. Wherever there is a solid line, notice pressure is on the y-axis, temperature is on the x. Wherever there is a solid line, that's an equilibrium place. Equilibrium means you can have two phases going on at the same time. Melting and freezing would be occurring at the same rates. Red line, that's where you've got vaporization and condensation in equilibrium, and deposition is where you have sublimation and deposition happening here at the same time in the green line. The triple point is where the temperature and pressure would have to be at in order to have all three states of matter present at the same time. So if you look at the liquid-vapor interface, that starts at that triple point where all three are at, and then you get to that critical point. Above that critical point, you see the vapor, liquid and vapor are indistinguishable from each other. So you see the triple point there, you have the liquid and the vapor up to that point. That's the critical point right up here. Once you get past that particular temperature and pressure, you can't tell the difference between the liquid and the gas. That's the critical. That's why it says supercritical fluid up here. A fluid could be a liquid or a gas. Once you get above that temperature pressure gradient into this area of the graph, can't tell the difference between the two. Each point along the line, that's the boiling point at that particular pressure. Notice that boiling point can change based on the pressure. So if the pressure is lower, it's going to boil at a lower temperature. The pressure is higher, it will boil at a higher temperature. Solid liquid, that's the melting point, and again, the melting temperature will vary based on the pressure. You can see that transition line in blue there. Below that triple point, it can't be a liquid anymore. It's either got to be a solid or a gas. That solid gas line, you've got equilibrium, sublimation, and deposition. Now this is an interesting diagram to interpret here for water. The triple point of water where all three phases could be at is where you see that very center here of the three lines. 0.00603 atmospheres and 0.0098 degrees Celsius. That is the triple point. That's an equilibrium spot. There's strong van der Waals forces, remember the water, hydrogen bonding that you've got going on. High critical temperature and high critical pressure. 374.4 Celsius. That's an abnormally high critical point up here at the top. Again, hydrogen bonding explains this. You see water, if it is at 1 atmosphere, where it would freeze at, it would freeze at about 0 degrees Celsius. 1 atmosphere is normal atmospheric pressure. If that pressure goes up to 100, up here at the top, notice it's pretty consistent, pretty close to 0. And again, strong intermolecular forces, hydrogen bonding. Slope of the solid liquid line, which is here. Solid liquid line here is negative. Pressure increase just below the melting point. The water goes from a solid to liquid. So there's a negative slope there to it, slightly. Carbon dioxide, another phase diagram, same features, but really much different here. This is really dealing with dispersion forces. It's a nonpolar molecule. So notice some differences here between the two phase diagrams. The triple point is here at negative 56.4, 5.11 atmospheres. Look how low that critical point is compared to water. Only 31.1 degrees Celsius and 73 atmospheres. Much less than that critical point. Look at what happens with that solid to gas phase, how much bigger that is. Sublimes at normal atmospheric pressures, dry ice going from solid directly to a gas. Again, it takes less energy to break apart those molecules because you have weaker intermolecular forces. Dispersion versus hydrogen bonding, it's really much easier for those molecules of carbon dioxide to be broken apart. The last part of the section of the chapter talks about LCDs, or liquid crystals. Liquid crystals have some traits of solids and liquids. If you take a look at this picture of this diagram, there's double bonds are really rigid and strong here, and you've got a polar functional group at the end of one. If you've got polar functional groups, they can almost line up with each other and stack easily. If you think about a liquid crystal display, they have more order in them than a regular liquid does. If you look at the liquid, everything's very random. Look at the liquid crystalline phase, how they can almost line up with charges in an LCD part. So again, it has more order than regular liquid because of those. It's got rigid double bonds, but it also has functional groups that can participate in some sort of van der Waals force, or more specifically hydrogen bonding for LCD displays. Again, pneumatic liquid crystals, they're only ordered in one dimension along the x-axis, or along the long axis, and then the smectic liquid crystals are in 2 dimensions. Notice how they can be lined up along 2 different axes. We won't get into the cholesterol liquid crystals. We'll talk more about those in the organic section. That stops us with our phase diagrams here for section number 6.